Assalamualaikum. So in this video, I'm going to present some signal conditioning methods. We need to do this signal conditioning because the output from sensors are normally very noisy. Okay, so we need to condition it so that it is easier for the signal to be processed. Okay, so in this part, I'm going to cover these two functions of signal conditioning, which are amplification and filter. Right, so the first one is amplification. So normally the amplification process is done using the operational amplifier or op-amp. And in this video, I'm going to cover these four types: inverting amplifier, non-inverting amplifier, differential, and instrumentation. So firstly, what are the properties of an op-amp? Okay, so first thing you need to know is there are no current going into the op-amp because we are considering that the input resistance of the op-amp is infinity. So for this branch, I is equivalent to 0. Okay, so that's the first property. So similarly, there is no current into this branch as well. Alright. The second property is the voltage here. Okay, so the voltage here is always equivalent to the voltage at this point. Okay, so these two voltage has to be the same in order to make the open loop gain to be infinity. So these are the two important rules when you deal with op-amp. Okay, so for example, you can see here, the current here is 0, which is the first property that I have mentioned just now. And the voltage at this terminal is 0 because it is directly connected to ground. So if the voltage here is 0, it means that the voltage here will also be 0. So that's why it says here that V at the negative terminal and at the positive terminal is 0. Okay, now let's look at this one. So again, no current into the op-amp, and then this node is directly connected to this voltage V in, which means that this node will also be equivalent to V in. Okay, so this node will be equivalent to this value of voltage. Okay, so you need to do nodal analysis in order to get what is the value of the gain and the value of V out. So let me show you one example on the derivation using nodal analysis. So let's look at the derivation when you are dealing with the inverting amplifier. So as I mentioned just now, the current into the op-amp is 0 and the voltage must be the same. So in this case, it is 0 volt. So if I do my KCL, so KCL going in is I in minus IF, okay, minus 0. So you can see that's the first line there, right? And then using branch current equation, so V in minus 0, because this node is 0 volt, over R1, which is the resistor here. And then IF is brought over to the right, which this is IF now. Okay, so the equation is 0 minus V out. This is my output voltage over RF. Okay, so if I rearrange, I will have the gain V out over V in equivalent to minus RF over R1. So this is called inverting because of this negative sign. It means that the output will be inverted. Okay, so that's why in this example, the gain is minus 10 because it's 100 over 10. So it's minus 10. Okay, 100 kilo ohm over 10 kilo ohm. Make sure the unit is the same. And so if my input voltage is 0.5, it will be amplified by a factor of minus 10, which means that the output will be minus 5. Okay, so that's why the output is minus 5. Right? So maybe you can try on how we can derive for the non-inverting using the same concept, and whether you can get the gain is 11 for this example, and whether you can get V out equivalent to 5.5. Okay. However, normally for sensors, we use two kinds of amplifiers. The first one is the differential amplifiers, and the next one is the instrumentation amplifiers. Okay, so let's look at the first one, differential amplifier, where it only responds to differential voltage that exists between two input terminals. Differential voltage means that the voltage is measured between two nodes. So that's why it says here, example of differential amplifier, it can be used when you use thermocouple, and you can see in the next few slides, I use it to amplify the strain gauge as well, because the output of that is also a differential voltage. Okay, so the main important thing about differential is the resistors RF over here must be equal, and then the resistor Ri here must also be equal. So the gain for differential is Rf over Ri. So these next two slides are showing the derivation of the equation. So the first statement here is VA must be equivalent to VB. That's the first rule, right? And there is no current into the op-amp. So I don't want to go too much into this because this is derivation. I will not ask question about derivation anyway because it's an open book exam. So I just want to highlight that eventually you will get this equation. So the V out is equivalent to the difference. You can see the difference in the voltage multiply with Rf over Ri. So this is the gain. Alright. So in this slide, the question also asks to prove by derivation. So this is the derivation step for the example just now to prove that V out equivalent to 10 multiply with the differential voltage. Okay. And what is the output voltage? If the voltage difference is 50 millivolts, the keyword is the voltage difference. Okay, so that's the keyword. So if V1 minus V2 is 50 millivolt, means that your V out will be equivalent to 500 millivolt, which is 0.5 volt. Okay, so this is the example where the differential amplifier is connected to a sensor. So in this case is a strain gauge. First, to calculate the value of the output voltage, which is this voltage, when the strain gauge reaches 102 ohm, okay, and then this differential voltage is connected to the differential amplifier here, and the question asks what is V out, okay. So let's do this together. So the first part of the question is asking you about the value of V. You have to go back and look at the strain gauge sensor and how to calculate the output voltage V. Right? So basically, since the positive terminal is here, it means that R4 will be the numerator and this term will be the first term minus this term over here, right? So it will be like this, right? R4 over 100 plus R4 minus 100 over 200. And you will have 102 because R4 has now reaches 102, and then you will get 4.95 times 10 to the power of minus 3 multiply with VI. VI is the power supply, which is 5, this voltage here. And so your V is equivalent to 0.0248 volt. Okay, so that's the voltage at the strain gauge. So now this voltage is being fed to your differential amplifier. So next you need to calculate what is the value of V out when the V here is connected to your differential amplifier. And Rf is given as 100k and R1 is 1 kilo ohm, right? So we know the gain for differential is Rf over R1, and you need to multiply with the differential voltage VB minus VA. Okay, so what you get, the gain is 100 over 1 is 100, VB minus VA is the voltage V, 0.0248, and you will get 2.48 volt. So that's how you solve this kind of question where you integrate the sensor with the amplifier. Okay, so the next amplifier is Instrumentation Amplifier, which is much better than the differential because it is ideal for measuring low-level signals in noisy environments without error, and you can also increase the gain by having this potentiometer here. Okay, so this potentiometer, you can play around with the values in order to increase the gain. Alright, this is the calculation of your output voltage. V out is equivalent to R3 over R2 multiplied with VB minus VA, and this VB minus VA, okay, which is these two values, alright, is this value here. Alright, so that is the equation for instrumentation amplifier. So let's look at the example. So this question stated that an instrumentation amplifier has a gain of 20 if R3 is 10 kilo ohm and R2 is 1 kilo ohm. The current through R1 is 4 milliampere and V prime is 1 volt, VA is minus 2 volt, and you are asked to find what is R gain and R1. Okay, so firstly R1 is pretty easy to find because you know these two voltage values. So the current is in this direction, so V prime minus VA over R1 is equivalent to 4 milliampere. Why is it 4 milliampere? Because there is no current into this branch. Okay, no current into the op-amp. So this is 4 milliampere, this is also 4 milliampere, and this is also 4 milliampere. So V prime minus VA over R1 is 4 milliampere, And that's how you can find R1. Okay. Next is finding your R gain. So to find your R gain, so this is the equation just now. Alright. So V out over V2 minus V1 left you with this equation. So this is the value of your gain. Alright. So you are given what is R3 and R2, and you are also given what is the value of gain, and you have calculated what is R1. So it's just a matter of mathematics to find what is your R gain. Okay. So in this example, again the amplifier is connected to the strain gauge, and this question gives the value of the output voltage, which means that it gives the value of your V out. So again, the strain gauge changes the resistance from 100 ohm to 102. So you need to calculate what is V, and this value of V is the value of V2 minus V1, the differential voltage. So the values of the resistors are given, and you are asked to calculate what is R gain. Okay. So similarly, you need to calculate what is the value of V, the output of the strain gauge. So this is the same method that I showed you in the previous example just now. You just need to know what is the equation, and you will find that the value of the voltage is 0.0248, just like the example with the differential amplifier. Okay. So now, the value of the differential voltage is fed here, okay, to the instrumentation amplifier, 0.0248 volt, and the output of your amplifier is given as 2.5 volt. It means that V out is 2.5 and V2 minus V1 is 0.0248 volt. Okay, so this is the equation. So if I rearrange my equation like this term is actually your gain, kan? Okay, just like the previous example. Let me show you. So this is the gain, right? So this is V out over V2 minus V1. Okay, so similarly in this case, right? So V out over V2 minus V1 is 2.5 over 0.0248, and you are left with this term, and then this is the values, okay, and you get 100.8, and then 100.8 minus 1 is 99.8, and then you will get R gain equivalent to 2 kilo ohm. Okay, so that is how you solve this example. Okay, so that is the end of the signal conditioning under amplification using op-amp, and mainly the final exam will ask about differential and instrumentation amplifiers, because those are the common amplifiers that I use with sensors. However, the main important thing you need to remember is the two rules of your op-amp. There are no currents into the op-amp, and the voltage at this non-inverting node and this node must be the same. So those are the two important characteristics of your op-amp. Okay, so thank you. Assalamualaikum.